Hello students, welcome to the 7th lecture on the topic sequence and series. So in the previous lecture we have left the proof of the Lebanese theorem. So quickly I'll write down what is Lebanese test and how you can prove the convergence of alternating series with the help of the Lebanese test. So I'll write it down quickly about the Lebanese test, and then we are going to prove it also. Or you can call it as an alternating series test. Okay, so the definition, like the theorem says that a series that is alternating means you have a positive and negative sign alternatively. So you have, suppose you have this alternating series converges if following three conditions are satisfied. So let us see what are those three conditions. So first condition is un, that is this should be greater than 0 for every n greater than or equal to n, that is n is some positive integer. And the second condition is un should be greater than or equal to un plus 1 for every n greater than, and this means that the un is non-increasing. And the third condition is limit n tending to infinity un is equal to 0. Now if any of the one conditions of the Lebanese test are not satisfied, we cannot apply the alternating series test to tell whether the series is convergent, the alternating series is convergent or divergent. So firstly we will prove this, and then we will do some examples related to this theorem. So let us prove. So for proving this, we need to consider the nth partial sum, that is you need to consider Sn, and this will be equal to this. You already know what does this nth partial sum means, and the last term will be, the nth term will be equal to this. So I call it my equation 1. Now I'll make two cases. So case 1 is when n is an even integer. So we will see when n, what happens when n is an even integer. So I can say n is equal to 2m for some positive m. M is positive integer. Okay, so what will be my Sn? This will be equal to S 2m. That will be equal to u1 minus u2 plus u3 till minus u2 m minus 2 plus u2 m minus 1 minus u2 m. I call it equation number 2. Now I can write this equation number 2 in two ways. So firstly consider this combination. So let me write down the first combination, that I can write this equation number 2 as this I call this as equation number 3. You can easily see that just I have paired first two, then other two, and so on. And you can also write this equation number 2 as this. I'll separate this u1 and then I am writing two terms together. So this will be and one term is left, that is u2m. Now this is my equation number 4. Now let us see what does this equation number 3 and 4 tell us. So just have a look that you have this condition that un is greater than or equal to un plus 1. So if I look at this, what will happen to this term? This will be either 0 or positive. 0 or positive. Similarly, this, because of condition 2, this will be 0 or positive. Similarly, each and every term will be either 0 or positive. So let us write what we observe from this equation number 3. So we can observe that S2m is sum of m non-negative, or you can say that it is a set of m positive terms. It may contain like 0 also, 0 or sum of 0 and positive terms. So this implies that S2m is less than or equal to S2m plus 2. Obviously, if I add 2 terms more, my S2m, since it is a sum of positive terms, so if I add 2 terms more, this S2m will be either less than or equal to S2m plus 2. Now I call this as equation number 5. I have my equation number 4, so I call this as equation number 5. Now this implies that, what does this implies again? This implies that S2m is non-decreasing. This is clear from this 5th equation that S2m is non-decreasing. Now let us see what does this equation number 4 tell us. Now if you look at equation number 4, this u1 is positive because un, you have written uns are greater than 0, so this term is positive, and the bracket term will be either 0 or positive because again from the second condition. So these are either 0 or positive. This is positive. This is again 0 or positive. Now you are subtracting u1 with so many numbers. So you can, this is obviously, this is positive, so this is again a negative term. So what can you conclude from equation number 4? I'll write that now from equation 4 we observe that S2m will be less than or equal to u1. It is clear that since the equality holds, now if I delete all these, like if I do not consider, then S2m will be less than or equal to u1. Equality will hold when all the terms are equal. So this is clear. So I'll get equation number 6. Now what does this imply? This implies that S2m is bounded from above. This implies that S2m is bounded from above. Now if I call this one as my A and this one as B, now if I combine this A and B, that S2m is non-decreasing and it is bounded from above, you know by non-decreasing theorem that it will converge. So I'll write it down, hence by non-decreasing sequence theorem, S2 and M will be convergent, because this is a sequence which is non-decreasing and this is bounded from above. So you have already studied this non-decreasing sequence theorem, and it says that S2m will converge. So that means that, so therefore you can find out the limit. Let us call that limit as L and say its equation number 7. Now we will consider, so keep this result, and then we will discuss case 2. If n is odd integer, say this is a odd integer where m is a positive integer. So now you can write S2m as then the sum of first nth partial sum, that is n terms of sequence this S2m plus 1 is, so this will be equal to S2m plus 1, which will be equal to u1 minus u2 plus u3 minus u4 u2m minus 1 minus of u2m plus, there will be also another term um plus 1. Okay, now you have seen already that this is equal to, you have written that this is equal to S2m. So I can write this as S2m plus u2m plus 1. This is my S2m plus 1. Now I'll take limit. Now I call this as equation number 8. Now taking the limit of equation number 8, therefore limit n tending to infinity S2m plus 1 equal to limit m tending to infinity S2m plus u2m plus 1. So this is equal to okay, so now you have already shown in 7 that this is equal to L. Now what about this? Now see condition number 3 of the statement that when these 3 conditions are satisfied, then only we can say that the alternating series are convergent. So from this limit un will be equal to 0, this limit will be equal to 0. So this comes from the third condition. So I have ultimately limit m tending to infinity s to m plus 1 is equal to L. Now this is my equation number 9. So now from equation number 7, this one and this one, what will you get? You have s to m is going to limit L and s to m plus 1 is going to limit L. This implies that Sn will also go to limit L. The sequence Sn will also go to the limit L. The even index and odd index, if go to same limit, the Sn will tend towards the limit L. Now what have you proved? That the sequence of partial sums is converging, so your original series will also converge. Therefore you will write, since sequence of partial sum is convergent. This you have shown from this, that the sequence of the partial sum is convergent. So therefore the series, that is your original series, is also convergent. So you have seen that you have used all the three conditions to get this result. So only if these three conditions are satisfied, you will apply, you can say that the series is convergent by the alternating series test. And if these conditions are not satisfied, you cannot say anything that whether the series is convergent or divergent. But this third condition, if it does not hold, it has an important role. We will discuss through the examples. So let us do some examples. So this is question number 1 for this Lebanese test. So check. Okay, so we need to check this is an alternating series, so you know that how to check the series is convergent or divergent by Lebanese test. So let's use that. So for the notation purpose, I'll write this and this is like if I separate the signs, I'll write this as this. Now this implies that un is equal to what? 1 upon this. Now see case 1, like condition 1, that un is greater than 0 for every n greater than or equal to 2. This is satisfying. Like this one is satisfying. You can see that this is un, it is greater than 0 for every n greater than 2. So you have a tick mark on the first condition. Now the second condition, let us look. So I want to see that whether it is non-increasing or decreasing. So I have two ways to find. If I do un minus of un plus 1, what will I get? This will be equal to okay. So now you can see that this one will be greater than 0, and what does this imply? This implies that un is greater than un plus 1, and this implies that un is decreasing. So we got a tick mark in the second condition also. You can prove it in the other way also, that you know that if you consider a function, like if you consider a function f of x is equal to, sorry, this will be ln of x. If you consider this function and if you find the derivative of this, you will get this. Now this is again less than 0 for every x greater than or equal to 2. Then from this also you can see that this is decreasing, and hence un is decreasing. Just I have discussed another way. You can use either this one, like to show that it is decreasing, or you can use this one. Now what about the third condition? So let us see that we are left with the third, checking the third condition. We will see limit n tending to infinity 1 by un. Now you can easily see that this is equal to 0, and therefore all three conditions of Lebanese theorem are fulfilled, and so is convergent. You have already proved that if all the conditions are satisfied, you can say that the alternating series is convergent. Now let us see another example. So you have this I'll write it for the notation purpose. This is equal to an, and this, if I take out the signs from it, I'll call it as un. Okay, now you want to check the whether it is convergent or divergent. So I'll use the Lebanese test. So first check that un is equal to, which is equal to 1 plus 1 by n. Clearly un is greater than 0 for every n greater than or equal to 1. It is clearly seen. So you have got one tick mark on this first condition, and then you need to check that whether it is decreasing or not. So for decreasing, you can take f of x, you can consider f of x, consider f of x is equal to 1 plus 1 by x. Now if you differentiate this, you will get minus 1 by x square, which is less than 0, and therefore f is decreasing for every x greater than or equal to 1. Hence you can say that the un is also decreasing. So this also satisfies. Now we are left with the third condition. Let us see what about the third condition. So if I find the limit of the un, this is equal to 1. Now see that this is saying that summation, this is not going to 0. So the third condition, therefore the third condition of alternating series test, I can write it as, or Lebanese test, is not satisfied, and therefore we cannot use the test to discuss the convergence of summation of an. I wrote this series as summation of an. So you have seen that this is not satisfied, so you cannot say anything about the convergence or divergence of this by the Lebanese test. Now you know Nth term test. Now if this condition is not satisfied, it says that an will not go to 0, and by Nth term test you can say that the series is divergent. You have already seen the Nth term test, and if the third condition, this is the importance of third condition, that if third condition doesn't hold true, then you can directly say that the alternating series is divergent. It happens only if the third condition does not hold. But if this first and second condition doesn't hold, then you cannot apply this Lebanese test. And by Nth term test, you can write, but by using Nth term test for divergence, since you can easily see that since limit of un is equal to 1, which is equal to what? Limit of this was our an. So I can write this as limit this. So therefore limit of n tending to infinity an will be equal to limit of n tending to infinity minus un, which is equal to this. So see, I have written this because I have used already an as minus 1. This is equal to this. So I have used this to find the limit of an. So why I am saying all this? Because what does this un not going to 0 implies that the nth term of the alternating series will also not exist. This implies that this will go to the limit of n tending to an will go to +1 and -1 if n is odd and n is even. So therefore this implies that limit of an does not exist, and therefore summation of an is divergent by nth term test for divergence. So I hope that this is clear, that why this third condition is important, that if it doesn't go to 0, then you can say that the series diverges by applying the nth term test. That means that the original alternating series will also diverge. Now we will move on to the next topic, that is absolute convergence. Now what does this absolute convergence mean? So I'll write it down and then I'll explain. A series is, this is an alternating series, is said to be absolutely convergent if is convergent. That means that the series of the absolute value also converges. Suppose that you have an alternating series and then you convert it into the series with all positive signs. Alternating series means what? That it has an alternative, negative and positive signs. Now if you put a mod, that means that you are converting all the signs as a positive. Now if that series is also convergent, you say that the series is absolutely convergent. That means that the alternating series is also convergent, and if you put mod, this is also convergent. For example, if I have this, now this is my alternating series. So if I find out the mod of this, what will I get? I'll get this. And now this implies what? Now this, you can see that this is a geometric series with r is equal to 1 by 3, which is less than 1, and therefore it is convergent. So you can see that the mod of an converges if you consider this an is an alternating series, and if you take mod, you have this series, and you can easily you know that this series converges as this is a geometric series with the common ratio 1 by 3, which is less than 1. So this is convergent, and ultimately I'll prove the theorem that if this is convergent, this one is also convergent. If the mod one is convergent, that if you make all the negative signs as positive, if that series is convergent, our alternating series is also convergent. And let's see some other examples also. Example 2 for this. Now if I have this series, this is under root n, now here you can easily see that what will be mod of an? This will be equal to 1 by under root n. Okay, so what about the nature of this series? This is divergent P series, as P is equal to half. So you have already seen that this type of series converges only if P is greater than 1, and it diverges for other values of P. So here the P value of P is half, so this is a divergent P series. So what is the nature of this mod n? This is divergent. So this is not, therefore is not absolutely convergent series. So this is not absolutely convergent, as this mod of an is divergent. So this is not absolutely convergent series. Now there is another type of series that is called as conditional convergent. So let us see what does this mean. Conditional convergence. So I'll write it down. A series is conditionally convergent if series an itself is convergent, but it is not convergent absolutely. Now what does this mean? This means that you have summation of an is convergent, but summation of mod an is not convergent. That is, if you consider the alternating series, that comes out to be convergent, but when you take the mod, that is, you make all the terms as positive, it becomes divergent. Then you say those type of series as conditionally convergent series. So let's take an example for this conditional convergent series. So you have this series, that is an alternating series, and you have to tell whether this is conditionally convergent or not. So I'll write it for notation purpose. This is an, this is equal to if you consider mod of an, consider this mod of an, so what will be the value of this? This will be equal to, from 2 to infinity this will be, and from 2 to infinity this term, all positive terms. So now we have to look for the nature of this series. Now you know how to look for the nature of the series with all terms positive. You can apply limit comparison test, you can apply direct comparison test, ratio test, and so on. So I'll apply this limit comparison test to check the convergence or divergence of this. So for this I'll let Bn as summation of Bn will be equal to 1. So you know how to apply limit comparison test. You choose this, and this is divergent. You already know that this is divergent P series with P equal to 1. You have already shown it as divergent by using integral test. Now if I find out mod of an by Bn, what will I get? I'll get limit n tending to infinity ln n, which is equal to, because n got cancelled out, and this will be equal to infinite. Now you can see that the value of the limit is infinite and Bn is divergent, and therefore an, mod of an will be also divergent. So therefore now I'll write it completely. Now since summation of Bn is divergent, so by limit comparison test, summation of mod an will be also divergent. So it is clear that mod of an is not convergent. So what can we say? That it is not absolutely convergent. So this implies that an is not absolutely convergent. Not absolutely. So we are sure, because mod is not convergent, so it is not absolutely convergent. Now what about the conditional convergent? For conditional convergent, we have to show that this alternating series converges and this does not. We have done the half part, that mod of an is not converging, but we still don't know what is the nature of this alternating series. So we have to check this by applying the Lebanese test. So let's apply the Lebanese test. I'll write it down to check To check whether summation of an, that is our alternating series, is convergent or not, we will use Lebanese theorem or alternating series test. So first condition, again we have to check that un, that is equal to this, is greater than 0. Obviously it is greater than 0 for every n greater than or equal to 2, because the series starts from 2. So it is okay that un is greater than 0. Now what about it's decreasing or not? So let us check by considering function fx, and then f dash x will be equal to, now this will be less than 0. If x is greater than, this implies that this will be less than 0 when x is greater than the exponential, that is something 2.7, or you can say 3. So you have found out n, that for every n after this value the function will decrease. So you can write, I'll write next page. So f is decreasing function for every x greater than e, that is equal to 2.7. So f is decreasing, so there is no harm. So the second condition is also satisfied, that it is decreasing for x greater than or equal to 3, you can say. Now what about the third condition? So let's check the third condition. What about the limit? So the limit of this is, you can see this is infinity by infinity form. So if I apply the L'Hopital rule, what will I get? This equal to 0. Now since all three conditions of test are satisfied, hence summation of an is convergent. So now what does this imply? This implies that it is conditionally convergent. Which series is conditionally convergent? We are talking about this series. So if we see this series, we will say that this is conditionally convergent, as if we take mod, it is coming to be divergent, that if we replace all the negative sign with the positive sign, so we get this series, and this series is divergent, so it is not absolutely convergent. Then we check for what about the nature of the alternating series. So for this we have this test, Lebanese test, which we discussed, and we see that all the three conditions are satisfied. So this alternating series will be convergent. So the series is conditionally convergent and it is not absolutely convergent. So now there are some observations which we have seen from this. So I'll write down those observations. What are the observations? That if some mod of an is convergent, this implies that summation of this will be also convergent. We will prove this. And the second thing is that if mod of an is not convergent, then we can have two cases, that is, first summation of an is convergent. Summation of an means the alternating series. If mod is not convergent, then it is possible that the alternating series is convergent, and therefore we will say this as conditionally convergent. Okay, and the second case is if mod of an is divergent, then this can be also the case if that mod is not convergent. If you see the alternating series, that is also not convergent. So then you will say that the series is overall divergent. And if alternating series is convergent, this is not, this is conditional convergent. Okay, so now we are going to prove this, that if mod is convergent, like alternating series is automatically convergent. So let us prove this. The proof is simple. This is called as absolute convergence test. So if okay, so it says that if mod is convergent, then the series, that is the original series, also converges. So let us prove this. Now you can see that I can write an can be written as this. I can write an as this. I have added and subtracted this mod of an, and if you already know that, you can write this as okay. So now what is given? This is given, that if mod of an converges, so that means that this converges. We have one term that is convergent. Now we have to look for the nature of this, that what about the convergence, that whether this term is this series is convergent or divergent. So let's have a look. So if we consider this, and we already know that I'll write that to check convergence of this term. Okay, so since you already know that this inequality holds, obviously this is an alternating containing alternating terms, positive and negative. So if I put all mod, this will be less than and this will be, so this inequality will hold true. And if I add an in all the inequality, what I will get? Mod of an if I add this. Okay, so now what does this say? You already know that this is convergent. It is given. So k of this is also convergent. That will converge to whatever the value this is converging to, multiplied by that value, this the total series will also converge, and therefore this will also converge. Now we can write that since mod of an is convergent, so 2 of mod of an will also be convergent. You can write it from n to infinity. So this will be also convergent, hence by direct comparison test, summation of n from 1 to infinity an plus mod of an will be also convergent. Okay, so now you have found that this is convergent and this is convergent, this is already given. So the subtraction of two convergent series is also convergent and hence an is also convergent. So you can write that mod of an is convergent and this is also convergent. Difference of two convergent series is also convergent and therefore summation of an is convergent. I hope this is clear because this one is convergent, this one is convergent, so this one is also convergent. So now you have proved that if this one is convergent, the alternating series also converges. So this is very helpful. Like if you are asked for whether the series is convergent, absolutely convergent or conditional convergent, so you can start by finding out the mod of an. So let's have a look on few examples. Or I'll do this example on the next class because we are running out of time. So I'll discuss the examples for this on the next class. Thank you.